Hello friends, welcome back to your channel. In this channel, we try to solve the previous year's physics questions of Neet UG exam. This is also helpful for those aspirants writing the JEE mains exam. This is solved in a very student-friendly manner so that you can understand and apply the concepts. We have included all types of questions appearing in the exams so that your preparation is complete. If you like the content, we urge you to like the videos, subscribe to the channel. This motivates us to create more content for you and help you in your exam preparation. We also urge you to subscribe to the channel so that you are immediately informed of any content added to the channel. If you have any doubts, then please feel free to add in the comment section. We will try to revert to you at the earliest possible. So without much ado, let's get started. So in the previous in the previous video, we had shared the questions to be solved for rotational motion 2. There are 10 questions we had shared, and we will be solving these questions now. But before we go there, I think it will be helpful to go through some basic concepts which will help you understand how these questions are to be solved. Okay? So first we'll go through some concepts. One of the key important things we first encounter in rotational motion is the moment of inertia here. Okay. Now, if I just take you back to a linear motion, we had this entity called mass. Okay, this was required for linear motion. Now, what is mass in terms of linear motion? Now, we know that force is equal to mass into acceleration. Okay, so if I have to move a certain body which is lying at rest, imagine it is lying at rest on the surface of Earth, for example. If we have to move this from here, right, and give it some acceleration, then mass is basically the inertia of the body. It is the resistance of the body towards the force. If I have to apply some force in order to move this, then mass is the resistance of this object to any change in its state from zero velocity to or zero speed to any linear motion. So similar to that, we have moment of inertia, right? So moment of inertia is very analogous to what we had in mass in the case of linear motion. So how is the moment of inertia defined? So I is equal to, as we have mentioned here, if there, for example, if there are multiple particles in a system, okay, and if you have to give some rotational motion to it, okay, then if imagine there are too many bodies here, right? So each of them will have a certain radius or distance from the rotational axis, right? So if this is the rotational axis, so each of these bodies has a certain distance from the rotational axis. So I is equal to summation of mi to ri square. So what does it mean? If we have n number of bodies here, this will be equal to sum of m1 r1 square plus m2 r2 square plus m3 r3 square and so on and so forth, right? So this becomes a moment of inertia. Okay, so moment of inertia, similarly, just like we had mass in linear motion, it represents the resistance of an object to the change in its rotational motion. Okay, so it depends on the mass, and the distance of the mass. So what did it depend on? We saw the mass is here and we saw the distance, right? So imagine each of them has a mass here, say m1, m2 and so on, right, m3 and so on. So it depended on the mass and the distance of the mass from the perpendicular axis around which the body is rotating. So the body is rotating around this. It depends on the mass and the distance square. Okay, so this was about the moment of inertia. Now the next term which we encounter is the angular momentum. Okay, so what is the angular momentum? The angular momentum now, if you remember in the linear motion also, we had this P is equal to mass into the velocity, okay, or the speed. Okay, so this was the linear momentum. P is mv. Okay, and it used to be conserved. It will not change unless an external force is applied on it, right? So imagine if a ball is moving, like this, it will have the same momentum unless there is an external force applied on this, right? The linear momentum used to be conserved. It will not change, right? Similar to that, even in the case of angular momentum also, the angular momentum will be conserved. It will be conserved just like the linear motion, unless there is any external force acting on the body. Okay, unless an external force acting on the body. So now let's, in that context, imagine these two entities, who are standing on the ground here and who are rotating around, say for example they're rotating like this, right, axis perpendicular to this, and they are standing just next to this axis. So in this case, for example, what will the I be here? Because you see, if I just take it crudely as a system of particles, so some of the particles or some of the masses are away from this, right? So L is equal to I omega, right? L is equal to I omega. Now this is if you remember, this is very analogous to what we have. P is equal to mv. Okay, so leaving aside that now, so L is equal to I omega. If for example, if the body is spread out like this, right? If the body is spread out like, and if it is rotating like this, then I will obviously be more, because I is mr square. Okay, I is mr square. So if it is rotating and the distance is more, right, or the distance of these particles are more from this axis, then I will be more. In that case, it will be rotating with a lesser angular speed. Now, but if, say for example, this person or this entity holds its hand straight, like in this case, what will happen is that then, since we know that the angular momentum is conserved, the I will become smaller, because now the R is much smaller, right? The R from this axis is much smaller, okay, this axis. So since this has become small now, so I will be less. Now the angular speed will become more. So L is equal to I omega. So I think this is one key important thing which you need to know for your NEET exams, because angular momentum conservation is a very key topic which keeps coming very often. Okay. So next formula, what we need to know is tau. We already have gone through this earlier, which is tau. We know what is tau. It is torque, right? I think all of you know about it. Torque is equal to I alpha. Now this is very analogous. If you remember, we had force is equal to mass into acceleration. This is very analogous to that. Okay, so tau is representing the force in rotational motion, and I, as we talked, it is representing the mass which we had in linear motion, and alpha is the angular acceleration. Similarly, we have Ek, which is the kinetic energy in rotational motion. It is given by half I omega square, which is very similar to what we had in linear motion, is half m v square. Okay, this was the rotation. This was the linear kinetic energy, and this is the rotational kinetic energy. I will go to the next one. Now these are some of the standard formula which you need to know, that what are the moment of inertia for different body shapes. So let's get started. So imagine if this is a ring. So I is equal to mr square is the moment of inertia for this case. If the axis is in the center, and if it's rotating around this axis, right? In the same ring, for example, if it is lying flat like this, and the axis is on the diameter, okay, is the diameter of the ring, then I becomes equal to half mr square. Okay, the same ring. So you can see here that the I depends on the axis through which the rotation is happening. In this case, the rotation is happening, the axis is perpendicular to the ring, so it is mr square. In this case, it is along the diameter to the ring, and it is half mr square. In case of a circular disc, it is half mr square, where the axis is perpendicular to the disc. For a solid cylinder, if the axis is perpendicular to solid cylinder like this, it is half mr square. For the same cylinder, but if it is hollow, right, and if it is thin walled cylinder, hollow cylinder, the I is equal to mr square. If you have rectangular plate like this, thin plate, in this case, I is equal to 1 by 12 m a square plus b square. So a is the breadth, for example, and b is the length here. If you have a solid sphere, it is 2 by 5 mr square, where r is the diameter of the sphere. Okay, so in this case also, right, r is the diameter of the ring. In this case, r is the diameter of the ring. Here also, r is the diameter of the disc. Okay, we're not given there, but I thought it was understood, right? In this case also, this is r, which is the diameter of the hollow cylinder and solid cylinder. In this case, this is a hollow sphere, and if the hollow sphere of radius r, right, this is represented by 2 by 3 mr square. This is the moment of inertia. In case if it is a thin rod, then it becomes 1 by 12 mr square. So thin rod, there could be two instances. One is that if the axis is somewhere in the center, perpendicular to the rod, in this case it is 1 by 12 mr square. But the same axis, if it goes to one end of the rod like this, right, then it becomes 1 by 3 mr square. Okay, where r in this case is the length of the rod, right? I am saying r is the length of the rod. In this case also, r is the length of the rod here. Okay, r the length of the rod. Now we go to the next set of concepts. The one important concept which comes very often is the parallel axis theorem and the perpendicular axis theorem. Now, what does it mean? For example, if we have this ring here, right, and we saw that the ring, for a ring we have I is equal to mr square if the axis goes through the center and it is perpendicular to this, right? So, but if this is a ring, for example, if this is a ring, then we said that I is equal to mr square. But if someone asks me, then what will be the I if, for example, it is a tangent to this, right? If you're tangent to this, then what will be, if they imagine the axis is perpendicular, axis is along the tangent, then what will be the I1? Okay, so in such cases we apply something called the parallel axis theorem. So in that case, it will be I is equal to center of mass, which is there originally. The axis is equal to I is equal to m, I center of mass, plus the distance, right? If this is a distance here, if this is r once again, so it will be mr square once again. Okay, if this is, say for example, mr square, then this also becomes mr square. Okay, so this becomes 2 mr square. Okay, so this is about the parallel, and this applies across all shapes. So even if you have disc also, the similar thing will happen, right? So whatever we have the inertia, moment of inertia for a disc, for example, right here we had, for example, for a disc we had half mr square. So if the same if the axis is passing through the center, it is half mr square for a disc. But if the same axis is passing through the tangent of the disc, it will become half mr square plus mr square. So the same thing will apply, similar thing will apply there. So this was about the parallel axis theorem. So now we'll go to something called a perpendicular axis theorem. Now what does perpendicular axis theorem mean is that, just clear this off. So perpendicular axis, what does it mean? For example, if we have these three axes, right, we have ix, iy, iz, right? So ix is the moment of inertia along the x-axis, iy is the moment of inertia along the y-axis, and iz is the moment of inertia along the z-axis, right? So what the perpendicular axis theorem says is that Iz is equal to Ix plus Iy. Okay, so this we have a problem which we will explain you, which will get into more detail that how does it work. But imagine, just to give you a small brief, right, that if we know, so for example, right, we know that Ix, for example, for a ring, right, for a ring, it is, for example, for a ring, if this is equal to mr square, okay, if a ring is equal to mr square, and if we have to find for some other axis, for example, then we can apply this set of theorems to get to the formula for finding the I or the moment of inertia around the different axis. We'll get to a problem in later in which we'll explain in more detail. Okay, so now having said that, now let's get to some more concepts. So there's something called a radius of gyration. Now what is the radius of gyration? Radius of gyration is defined, so this is the radial distance from the center of mass of a body about an axis through the center of mass without changing an I. Means the I should be constant. Okay, I should be constant. The k, this we also represent by k, for example. So if I is equal to mk square, okay, k is the radius of gyration. So this is supposed to be a point mass. This is supposed to be a point mass somewhere. It could be anywhere, right? We don't know, which will be coming by computing. So if this is, for example, k, if this is k, which is this is a radius of gyration, for example, right? Now it is such that the I is unchanged. So I, for this object, what will be the moment of inertia? It will be, if I imagine the system of masses, we have, for example, m1, we have, say, m2, sorry, not this one. So we have m2, we have m3, and we have m4 here. Okay, so imagine a system of masses. There are 4 masses here. So for this body, we have I is equal to, so this is rotating around this axis, right? So this, for example, it will rotate around this one, correct? This will rotate around like this. Okay, and similarly for all these bodies, they rotate around this axis. So for this, what is the I, the moment of inertia, is m1 r1 square plus m2 r2 square plus m3 r3 square plus, and so on. Okay, now radius of gyration says that mk square is the sum of this, means the same moment of inertia is equal to mk square, and that is how you compute k. So let's take for 2 different cases. This is just examples, but this can be extended to other body shapes also. So imagine if we have a solid sphere. We know that for a solid sphere, if the axis goes to the center, okay, then we know that I is equal to 2 by 5 mr square. So 2 by 5 mr square is equal to mk square, the radius of gyration. So in this case, we want to find what is the radius of gyration. So 2 by 5 mr square is equal to mk square. So in this case, k becomes root of 2 by 5 into r. Okay, so this becomes the radius of gyration. What happens in the case of a hollow cylinder? In the case of hollow cylinder, mr square is the moment of inertia. This is equal to mk square, which is k is the radius of gyration. So in this case, k is equal to r. So in this, it means that the radius of gyration is same as the radius of the hollow cylinder. Okay, so now that we have got a good grasp on the concepts, now we can move to the problem, solving the problems. So this is the first question. Okay, the first question is given that a rod AB of mass m and length L is hinged at the end A. Okay, it is hinged at the end A. The rod is, okay, a rod AB of mass m and length hinged at the end A. Okay, the rod is kept horizontal by a massless string tied to the body. Okay, sorry, this is wrong. This should have been A and this should have been B. Okay, so there is a typo for that. Sorry for that. Okay, so a rod AB of mass, so the string, so there is string tied here. Okay, imagine that there is string which is tied like this to keep it from falling. So it is hinged here at point A. So this rod is tied here by massless string. It is side when the string is cut. If the string is cut, then what? If the string is cut, what is the initial angular acceleration of the rod? Okay. Now, if you look at this rod, right, where does the center of gravity act on this? The center of gravity acts on this. If this is L, this will be L by 2. Okay, L by 2. So, what will be the tau in this case? So tau means what? If this is released, for example, right? So this basically it means there will be a force acting on this, which is CG. This, right? There is CG acting on this, right? So this is a rod, for example. What I'm trying to say, and this is hinged here. If this string is cut here, this string is cut from here, it will try to fall, and there is a G acting on this, right? Which is a weight of the rod, which will be acting somewhere near the center because this is a symmetrical rod. And where will this act? This will act at a distance of L by 2 from here. Okay. So it means that tau is equal to I alpha. We know this, right? And so what is tau is alpha. Now what is tau is equal to the force into the distance as well, right? So force, what is the weight? Force is the weight, right, into L by 2. L by 2 is the distance where it is acting, right? So basically the force acting around this. So this is L by 2 here, right? As you mentioned here. So mg into L by 2 is equal to the I into alpha. Now let's go back to the previous section. What do we have here? What do we have here? For a rod, if in this case this is a rod, and it is supposed to rotate around one of its ends, right? So I is equal to 1 by 3 mr square. Okay, so this is equal to 1 by 3 mr square into alpha. Okay, means mg into L by 2 is equal to mr square by 3 into alpha. Okay, so gets cut here. Okay, and L is nothing but the R itself, right? So L is nothing but the R. So let me just erase this part here. I can write that this is R. This becomes R. This gets cut here. Okay, so it means alpha is equal to 3G by 3G by 2R. 2R, and R is nothing but the L here, right? R is nothing but the L. So R 3G by 2L. Okay. So this is the answer here. This is given here, the second one. Okay. Let's go to the next problem now. The instantaneous angular acceleration of a point, so theta is given by 3t cube minus 4t square. Okay, 3t cube minus 4t square. We want to know at what time will the torque on the wheel become 0. So torque has to become 0. Now what is torque is equal to torque? Torque we know is I into alpha. We know this, right? And what is I? I we know that m, depending on the body, right? It is some function of r, right? Could be some function of r into alpha. Now, if torque has to be 0, since the m here, this cannot be 0. This and r will not be 0. What could be 0 is the alpha. This could be 0, right? So for the alpha to be 0, which is the angular acceleration, it means for this body, this angular acceleration of this has to be 0. Okay. So d theta t is equal to this. So d theta dt is equal to the angular velocity in 9t square minus 8t. And what is the angular acceleration? Angular acceleration d2 theta by dt2 is equal to 18t minus 8 is equal to 0, right? Because if alpha has to be 0, then this has to be 0. It means t is equal to 8 by 18, 4 by 9 is equal to 4 by 9 second. Okay, this is the answer. So the answer is the third option here. Okay, so the answer is third option here. Okay, let's go to the next problem now. Okay, in the next question it's given that a solid cylinder of mass 40 kgs, mass 40 kgs and radius this is free to rotate about the horizontal axis. Now imagine this is the horizontal axis, right? This is horizontal axis here. Okay, if this is the horizontal axis, right, this is horizontal axis here, the mass and the radius are given to me. The mass is equal to 40 kg. Okay, radius is equal to 0.4 meter. Okay, 4 meter. The massless string is moved around the. Now imagine if this is pulled, what will happen? Imagine if there is a tension T. Okay, it is pulled. So if the tension is T, then it will actually make the cylinder rotate like this, right? It will make the cylinder rotate like this because the string will be pulled or rope will be pulled. Because of this will actually try to make the cylinder rotate around its horizontal axis. Okay, in this the alpha is given to be 6 revolutions per second square. Alpha is given to be 6 per second square. Okay, so alpha is 6 revolutions per second square. So 6 revolutions means what? 6 into 2 pi radians per second square. So everything is given in terms of pi here, right? So we need to calculate in terms of pi. So this is 12 pi radians per second square. Okay. So now tau, we know that tau is equal to I into alpha. Okay. And we also know that I for cylinder is equal to m square by 2. Okay, so half into m is 40 kg into r is given to be 0.4 whole square. Okay, so in this case I, so 220 and this is 0.16, so this becomes 3.2. This is I. Okay, so tau is equal to I alpha. We know this formula here. Okay, tau is I alpha, and also tau. What is tau here? So if you look at this cylinder, if I look at from this side, if I am looking at a cylinder from this side, so imagine that this is the crossing a cylinder. The tension T is acting like this, right? The tension T is acting like this, and this is a radius. So I can say that torque is equal to tension T into the R. Okay, right? T into R. So I can say that T into R is equal to I into alpha. Okay, I need to find the tension T. So T is equal to I into alpha divided by R. I always computed it as 3.2. Okay, and alpha is given to be we calculate it as 12 pi. Okay. R, that is the radius, is given to be 0.4. So if you just put this here, is equal to 96 pi. Okay, so this is the answer. This is the tension. Okay, so we will now go to the next problem now. Now look at this question. In this case, it is given that a uniform circular disc of radius 40 centimeters are red. So radius is given to be 40 centimeters. Okay, so radius is equal to 0.4 meters. Okay, radius is given to us that the torque. Now this is the angular the axis of rotation. It passes through the center. The angular acceleration which is produced, it is angular acceleration which is 1 radian per second square. One important thing you need to notice is that the acceleration is changing here. Okay, the acceleration is changing because of this torque. Okay, so just to give you a brief on this, so imagine that the disk is like this, right, and it is made to rotate like this. So there is a centripetal acceleration which is acting towards the center of the disk. There is a tangential acceleration which is acting on the tangent of the disk, right, and the resultant acceleration, or which is the net acceleration, will be a, which is given here. Okay, so we'll have to calculate both of them, and then we'll have to find the net acceleration. So now if you remember the formula, W, we have to find the, so W is equal to W0 plus alpha T. Okay, what is W? We need to find the angular velocity. Okay, this is equal to 0, this is 0 plus alpha is given to us, which is 1 radians per second square, and T we need to find out the velocity after 3 seconds. So it becomes 3 here, so this becomes 3. Now what is the tangential acceleration here? We need to find out the tangential acceleration, right? Tangential acceleration equal to Et will equal to alpha r. Okay, so alpha is given to us is 1 radian per second square. Alpha is given to us, this is alpha here, alpha is 1, and r is given to us as 0.4. so this is tangential acceleration, which is 0.4. What is centripetal acceleration? Centripetal acceleration is equal to AC is equal to r omega square. Okay, and working value of this is a 0.4 into omega. Omega is 3 square. Omega square is 3 square. So this becomes 0.4 into 9, which is 3.6. So now, if you look at this, this is the how do you find this? This will be the hypotenuse, right? This is the resultant of this is 80 here. So the net acceleration, because they are acting in two perpendicular directions, so net will be the square root of the sum of them, right? So this will equal to 0.4 square plus 3.6 square. So this becomes 0.16 plus 12.96. Okay, this is roughly equal to 13.12, which is equal to 3.7. Okay, so the answer will be 3.7 meters per second square. So this will be the answer. So if you look at the third option, the answer is given to us in the third option. So friends, we have solved the first 4 questions here. So I think this video has got a little elongated. I'll have to stop here. So we have solved the first 4 questions. In the next video, we'll solve the rest 6 questions. If you think you are learning something from these videos, we'll request you to kindly subscribe to this channel and like the videos, because that will inspire us to create more educational content for you and help you in your NEET and JEE Mains preparation. Okay, so thank you. We'll meet you in the next video.